Hello, hello. Hello, hello. Okay, I think we fixed things. I'm gonna have a do-over. Oh wait, now my face is small. Hello. It's really good to have everyone here. Oh my goodness, Adam, it's so good to see you. It's so good to have you on stream here. Let's go and see if we can make my face big. Let's see. Layouts. I do not want to crop solo layout. Boom. Okay, we're back, and maybe I'll. Hi Zane, what's up with you? Oh no, Zanil. I am having a great time, and Adam's about to go to sleep, and I'm going to try to redo the intro kalimba because I did not realize there was going to be some background music that just started playing there. Okay, we can actually start now. Hello. My name is Will. I am a coach at Major League Hacking, a software engineer at Google, an avid Python enthusiast, and I'm also getting into chess, which is why I'm really excited for this stream because we are going to be teaching a machine learning model to play chess, and it's going to be a blast. So I am so glad that you are here. Per usual. Oh, hello. Fix the lighting. I'm going to drop our little form so that you can check in here and get credit for being here. And also, we'll talk more about this in a second, but I'm also going to redrop a link to a site called Kaggle, which we will dive into more. Boom. That'll kind of be our home base we're doing this stream, and then we're doing another stream on Friday after everybody gets a chance to build their best model to play chess, so to speak. So welcome. Yeah, chess is very popular all of a sudden. Yeah, so we'll get into chess and why it's popular and not popular, and whether or not you're a nerd if you're into chess, and whether or not it's embarrassing to be really bad at chess, because that's where I'm at right now. But we will maybe wait one more minute so that we are not jumping the gun here. But let's see. I already did my intro. Let's see. Drop in the chat. I have two questions. Drop in the chat if I've seen you on stream before. Like if we've interacted on stream, let me know you're here because it's always fun to know people are repeat guests. And then also let me know what you are drinking if you have any beverage. So I right now am drinking some Earl Grey tea. I know historically, I have been a big coffee proponent, and I still am. I think coffee is really good, and I think coffee is better than tea. In fact, this Wednesday, we're going to be doing a special Global Hack Week Games edition of Hack Your Coffee. So this Wednesday at this same time, join me on stream, and we'll drink some coffee and try to guess where it came from. But recently, I've been trying to cut back on my caffeine consumption, and I still want something just like warm in my hands to drink. And so for me right now, that is tea. Hello. Me and Mr. Mustard is also terrible at chess, and I appreciate the solidarity. Thank you, me and Mr. Mustard. I don't think I've ever seen Adam Drummond. Is that how you say your last name? I don't know who you are. I'm just kidding. It's good to see you, Adam. Hardo Moto, it's so great to have you here for your first time. New York's finest tap water. Love that. Stay hydrated. Micro shrimps. Oh yes. Oh yeah, like the little floaties in the water. Yeah, good stuff. I'm hearing a lot about rats in New York these days, which like my understanding is rats have always been in New York, but people are sure talking about the rats in New York a lot. Adam, the point is not that it doesn't have caffeine. It has less caffeine than coffee, my guy. I thought you were supposed to know things about caffeinated beverages. Hello, Arkham. Oh, also, if I ever say your name on stream and I say it incorrectly, feel free to correct me and drop a phonetic pronunciation in the chat. Also, please do let me know in the chat if I am going too fast. We are going to be diving into code and dealing with some machine learning models, and all of that can go really quick. And so please let me know if you have any questions. We will slow down. If you are new to this, if you have not used much Python, if you don't know much about chess, just please drop all your questions in the chat and we will get to all of them. It's why we have shrimp posture. Shrimp posture, is that like bending over like this? I would believe it. Okay, so without further ado, we are going to start sharing screen and hop over to Kaggle. And let's see, can I just grab, boom. Let me just set up the screen I'm about to share, and we will jump over to the punch in. Boom. That's pretty funny. Shrimp posture. I feel like I have shrimp posture sometimes. Okay, so this is, and I'll drop this link again. This is a website called Kaggle. Full disclosure, I'm now, Kaggle I think Kaggle is technically a subsidiary of Google, and I have been doing some 20% work with them. So I am not a totally unbiased person with respect to Kaggle. But Kaggle is this great platform for doing machine learning competitions. And so these competitions are usually of the form of they give you some data and they're asking you to make some kind of prediction. So a classic Kaggle competition is given some data on how much houses have sold for in the past, try to predict the value of new houses on the market, things like that. And so we are, for this session and the session on Friday, we are going to be doing all this work through Kaggle because it gives us a really nice sort of environment to train machine learning models and test them. And notably, it makes it so that we all have the exact same environment. And so when you write some code, it's exactly the same as the code that, or it's working in the same environment as the code that I write. So we're going to get in and actually look at some stuff. So first, let's take a look at the data. So our goal here is to build a model that can play chess, right? I want to get in and actually play chess against an AI. And so what we have to do is we have to build some system that looks at a chessboard and then tells us what move to make, right? We're going from a chessboard to a move. That's ultimately the machine learning model that we're going to build. And so if we come over to data right here. Oh, also, I believe that in order to actually look at the data, you will have to actually join our competition. And so I will maybe I will vamp for a second. If you want to create a Kaggle account so that you can actually get in and check out this data, I would highly recommend it, especially if you are interested in machine learning and things like training AIs to play chess. It's a really, really nice platform to use, and it actually gives you a lot of free GPU time. If you are familiar with this idea that in order to train really powerful AI models, you need tons of GPUs, and GPUs are really expensive. And Kaggle gives you like 20 hours of GPU time for free every week. So that is actually a pretty sweet deal. So I will, I guess this is me vamping. So I also will put on my flower crown. Nobody asked me to put on my flower crown today, but that is usually a thing I do when it's Global Hack Week. Boom, flower crown on. Okay, cool. So hopefully, if you are joining us and diving in, you have signed up for Kaggle. But if not, you are more than welcome to just sort of join. You can still see all the code, and you can watch me sort of code along through the stream. So no pressure either way. So we'll zoom in a little bit. Let me know if I can zoom in more, if things are visible, if everything's going okay. So if we come over here, we've clicked on data, and we've come down to train. We can see basically it's like an Excel sheet or like a CSV is what it's called. And we have a couple columns in here. We have this random ID. So we have a bunch of different potential boards that you could look at. Then this is our column that says board. And if this looks really confusing to you right now, don't worry. That's what we're going to spend our first chunk of time today actually talking about. Then we have something called black score, which we'll talk about more. But the short version is this is sort of how good this board looks for the side playing black. In chess, we have one side that plays as white and one side that plays as black. And so this is basically what does the score look like for black. And then finally, we have what's called best move. So there is a thing called Stockfish that is a really powerful sort of chess AI agent. And so this is basically, think of it like a chess expert saying, given this situation, this is the move that I would recommend. So this is our training data, but I want to dive into what does this board mean? So what we're going to do is come over to code right here. Oh, there we go. And so I already have written up 3 little notebooks that we are going to be using. And this is basically the guide that I'm going to be following. But just so we're sort of new minting things, I'm actually going to click New Notebook. And you are welcome to either do a fresh notebook or follow along with this one that's kind of already published. And that's kind of going to be the guide here. Actually, you know what? Maybe I will just use this notebook. So something that you're able to do is borrow my code to start as sort of a jumping off point. And so if you click right here instead of edit, you should see something that says like fork and edit or something like that. So you can create your own copy of this notebook. And a notebook is just a really convenient way to play around with some code and see what it does really quickly without having to go and save a file and get in your terminal and build an executable. We could just see what our code does instantly. So I'm going to click edit here and we will play around. So this is part 1, and we are going to understand this package called Python chess, which will be sort of our portal to chess rules, and talking about what an FEN, a Forsyth Edwards notation chessboard is. And if that's like totally confusing, do not worry at all. We are going to get into it. So this is what's called a Kaggle notebook. I'm going to hide this right here just so we can stay focused. Actually, I'm going to bring it back because it helps the spacing. Oh, Adam, congrats on getting selected for 30 under 30 over there. That's very, very exciting. Okay, cool. So this is what is called a notebook. If you've used a Jupyter notebook before, then this should look pretty familiar. This is basically a Jupyter notebook. So we have little bits of text that you can click on. And if you hit Shift and Return, then it'll like run the code for you. So the first thing we're going to do is we're going to click into this first cell and click Shift Enter. And all this line of code is doing is installing a package for us. So there's this package called Python chess that gives us a lot of really nice utilities. It lets us render boards really nicely, and it lets us basically make it feel real, sort of, and gives us a lot of help with the rules of chess. Also, if anybody is having any issue either like logging into Kaggle or forking this notebook, let me know, and I'm happy to help us debug. If you are sort of following along and you're able to run this first cell of code, then you are in a great place. Oh, also, I shouldn't bury the lead here. Kaggle is super fun, and I really, really love getting engagement on Kaggle. And so I am going to be giving away at least 2 swag drops. So one of the swag drops will be for the best notebook that somebody provides to this competition. And one of them will be for the best submission we get. And actually, we'll do a third, which is anybody who makes any submission, I will do a random raffle and swag drop somebody who made a submission. So there are 3 different ways to get swag drops in this competition. And none of them actually require that you, one of them requires that you win. Tomo says, will this make me a grandmaster? Yes. Okay. Yeah. So I'll actually mention this because you brought it up. So Kaggle has a very fun, they call it a progression system where you get ratings. And if you, it actually has some comparisons to chess where if you are really good and you show up every day and you are, writing good machine learning code, then you can gain the rank of Kaggle Grandmaster, which is a pretty cool thing to say that you are. Let's see, one who just said, can you please repeat how to fork? Absolutely. So we will jump back to, so if we jump back to this link right here, I'll jump there, then you should be able to come over to code right here. And it looks different for me because this is my model, this is my competition. But if you click on part 1, Understanding Python Chess and FEN, then for me, it just says edit, but right up here, you should see a button that says fork and edit. Let me know if that's not what you're seeing because it's been a minute, but that should get you in. And once you click on that, you should see a view kind of like this. But please let me know if anything was weird there. So all we've done by running this cell, you can also just plus the play button. Oh, also someone mentioned this is kind of like Colab, and it is actually exactly like Colab. Yeah, so Colab and a Kaggle notebook, they're both sort of different implementations of a Jupyter notebook. And they're really convenient ways to just play around and experiment with code. Oh, me and Mr. Mustard said copy and edit. Yes, that is exactly it. Okay, yeah, so look for the button that says copy and edit. Well done. Well done, community. Score 1. So we are just going to try to figure out how to play around with this Python chess library and what FEN means. So we've installed our Python chess library, and to actually start using it, we can just say import chess. So this is just the Python way of importing something, and then we can create a chess board by saying chess.board. Put some little parentheses outside of it. So this is basically telling Python, create a chessboard for me, and we'll store it in this variable called board. So we can run that. And so I'll do these actually separately. We can either print our board, and we get, it's a little bit small. Maybe we'll bump up one more size. This is maybe as big as I can go. But you can see kind of a representation of a chessboard. So if you are familiar, I think actually, I will drop, we're jumping around a little bit, but if we go back to this competition on the, let's see. Oh, wait, I think I actually have it up here. Oh, yes, okay. This is just a guide to how to play chess from chess.com that I think is a pretty good one. And boom. Hey, Adam, you weren't paying attention. Kaggle is owned by Google, so it's all Google all the way down. Okay, cool. So that is a great guide just to learn how to play chess. But in chess, there are lots of different pieces, and they are the rook, the knight, the bishop, the queen, the king, and the pawn. And so you can see that all these letters correspond to a different kind of piece. So R is for rook. Interestingly, knight is N instead of K. I guess it's just phonetic, and that's kind of nice. Bishop for B for bishop, Q for queen, K for king, and then P for pawn. And interestingly, the lowercase letters are for the black pieces, and the uppercase letters are for the white pieces. So this is just if we print out our board. So we say print and then wrap it in parentheses. But we can also just leave it at the end of the cell, and it will sort of render as a nice little picture. So hopefully this looks a lot cleaner than the little text board. Adam, you need to pay attention, my guy. We are using Kaggle because it lets us train and test our models in a competition. Come on, my guy. Okay, cool. So we have created our board, and also to be clear, everyone else is doing great. It's just Adam. We have created our board, and we can actually see it. So this is the starting position of every chess game. Every chess game starts like this. And one really nice thing that Python chess lets us do is that it actually will show us all of the legal moves that we can do. So if you go to that guide on how to play chess that I dropped in there, it'll walk you through what kinds of moves every piece can make. But sometimes it's kind of hard to know. There are some interesting sort of special rules, and so ultimately, it's really, really nice to be able to see all the legal moves that we can make. One detail about chess is that white always goes first. There's some social commentary in there, I'm sure. So if we just say for move in board.legal moves, we can iterate through all of them, and then we can print out our moves. And you might be thinking, whoa, what are those? Aren't moves. Those are like random letters and numbers, right? And this is what's called long algebraic notation. So there's going to be, if you have played chess before, you're like, this is just a board game. But we're going to be doing a lot of work to just get that game into a format that our AI can understand, right? Because our AI doesn't by default just know how chess works. We kind of have to tell it, well, this is what this looks like. And usually that means putting things into plain text. So what all these moves are and what long algebraic notation is it basically is comprised of two parts. We have our starting square and our ending square. So in this first move, G1 is our starting square, and then H3 is our ending square. So in this case, every move is 4 characters long, 2 parts, our starting square and our ending square. So I added some little context here, so in this case, C2, C3 means move the pawn from square C2 to C3. So we can actually unpack this. What does G1, H3 mean? Well, we can look for column G, which is right here, and then row 1, which is right here. So we're saying we're going to move our knight. That's the image for our knight. And then our 2 square is H3. And so H3 is over here. So the knight moves in this sort of L shape. And so G1, H3 means move your knight from right here to over here. Great. So that is long algebraic notation, and we just got a list of all our legal moves. Another really nice thing that Python chess lets us do is actually play out a move. So there is a command called push san, where we can actually just push that long algebraic notation. We're kind of in the details. There's a thing called short algebraic notation and then something else called long algebraic notation. But they're in many ways kind of interchangeable, so we don't want to get too deep into it. But we can call push san on this little move here, and we will get a board where something happened. Wow, look at that. We moved our pawn from C2 all the way up to C3. And that is a legal move for a pawn to make. So we have imported Python chess. We have looked at all of our legal moves. We have picked a legal move and actually played it, and we have seen the board sort of evolve. Do we have any questions? Are we feeling good about this? It's making sense. This is actually something else that I really, really wanted to ask folks. What is our level of Python familiarity like? Because I can sort of take it slower on the Python and explain more Python things. My request would be drop in the chat. Give me a 0 if you've never heard of Python. Give me a 1 if you've written like some Python before, but you're like, so. And give me a 2 if you're like, I'm a Python pro. I'm here to break some necks and cash some checks. Give me a 0, a 1, or a 2 in the chat. OMG, shout out to Ezriella, if that's not pronouncing it, because we got a 2. Oh, me, Mr. Mustard is a 2. Boom. Love that. Okay, so we have a lot of 2s, a lot of 1s. We got some 1.5s. Senjurak, thank you for being honest and saying 0. Hopefully most of this will make sense. And we will, even if you've never written Python before, if you just follow along, I will actually show you a place where you can really dig in and start playing with different models and hopefully try to sort of level up the machine learning model here in question. So we have gotten our board. We looked at our legal moves. Oh, so now, okay, thank you for weighing in on all of the legal moves. Oh, and also, Senjurak, I will take that comment off. Boom. Okay, cool. So what do our legal moves look like now? If we run the same chunk of code where we say for move in board.legalmoves, we actually get a different set of moves because now it's no longer white's turn, it's black's turn, right? So if we look at just G8, H6, that actually is this knight up here and going to H6 down here. So after the board sort of goes through one turn, it'll now tell us the legal moves for the other side. Great. So we can take a move like G7 to G5. If we come up here, we can see, okay, G7 is this pawn right here to G5. So another detail about chess is that a pawn is able to move 2 squares on its first move. So if a pawn hasn't moved at all before, it's allowed to jump 2 squares. Otherwise, it can only move 1. And so if we run that, we can push that, and we can see, boom, our pawn moved down. And a thing that is cool, obviously most of us actually know a little bit about chess, and we know that rule. But even if you didn't know that rule, our Python chess library told us that was a legal move. We love hackers helping hackers. Yeah, Python is, I think, a really, really lovely, easy language to learn. Oftentimes, when you write Python, it kind of reads like plain English, which I think is really nice. So yeah, as always, drop questions in the chat if you have them. But hopefully the Python part won't give you too much trouble, and we'll get into sort of the machine learning of it all. Okay, So we have played around. One last thing that we will talk about is board.outcome. So board.outcome just tells us if the game has finished. So there are a couple of ways that games can finish in chess. You can have, a simple stalemate, you can have a simple checkmate, which is where I'm attacking your king and you have no way to defend your king. Or you could end in a stalemate, which is where neither of us can beat the other person, or you could end in a draw, which is usually when like it'd be impossible for either person to win. So right now it says none if we print board.outcome. So we know the game isn't over yet, right? And obviously, like at this point, not that much has happened in the game. The game is not over. Okay, so now we have gotten our chess game going. We know how to place moves. Oh, Cedric, if you know how to code in JavaScript, I think that Python should not give you much trouble at all. Right on. So we've been talking about this thing called FEN, or Forsyth Edwards notation. You can go and click on the Wikipedia link if you want to get very academic. But this is the format that we are showing individual boards in our actual training data set. So if we say board.fen, we will get our fen out. Now, this should look familiar from our training set. It's a bunch of these letters, but some of them hopefully are a little bit less spooky now. For example, we know that this first R right here at the very beginning, that is our rook, right? So we're going to break this down piece by piece. This first part of our fen just shows us what's on the chessboard. So if you split right in this space right here, this whole chunk separated by slashes, this is our chessboard. Every row is separated with a slash, and so if we just replaced all of our slashes with new lines, our chessboard would kind of look like this. There's one more detail before this actually makes sense, which is instead of writing individual spaces, because there are just a lot of empty spaces on the board, one way that we can make our notation a little bit shorter is by replacing groups of spaces with a number. So this number 1 just means there's one space right there. That's pretty easy. And then 8 just means there's a whole row that's just empty. It's just 8 empty spaces. And so you can go through and you can kind of convince yourself this kind of looks like the board. And if we replaced all of the numbers with dots, that would actually give us just what our board looks like here, right? So our board down here kind of looks like the Forsyth Edwards notation, or the FEN, if we replaced all of the slashes with new lines. Do we have any questions about this first chunk of our FEN notation? Because honestly, it's about as deep as we're going to go on Forsyth Edwards notation. The rest of, actually, there's one other important part of your FEN, which is the second thing in your FEN. So the first big chunk is just what does your board look like. But then your second chunk will always be a W or a B. And that tells you whose turn is next. So right now, it's white's turn again, right? White went once, and then black went once, and now it's white's turn. So our FEN has a W in there. The next 3 fields, or no. The next 3 fields are kind of they deal with specific rules that we won't go into too much. But this next chunk, the KQ, the capital KQ, lowercase KQ, this means that both black and white can castle. So castling is this special move you can do in chess where you move your king and your rook at once. And so this just keeps track of can both sides castle. A dash, that second dash, means that right now there are no en passant takes. If you don't know what that is, don't worry, but it's like a special way that pawns can attack other pawns. And then 0 means that there have been 0 moves since a take, so like someone taking someone else's piece, or a pawn advancement. This is only important for a very specific rule we won't worry about too much. And then finally, so don't worry if these don't make that too much sense. You're free to look them up, but it's not really necessary for this notebook or this competition. I have a little typo. Necessary. That looks maybe correct. Then there is one final field in our FEN. This last number here is just the turn counter. It's just the number of turns that have passed since the beginning of the game. And so that, white went once and black went once, and so we get 1. And so we could even, just to see this kind of in action, we could say board. Let's look at our board. Actually, let's take a look at our board. So we know it's white's turn. Something that we could do is if we moved our knight from G1 to F3, we could threaten black's pawn. So threatening is when you have a piece that on the next move could take someone else's piece. And so in general, you want to try to, you want to try to take other people's pieces and you want to threaten them. So we could say board push san, and then we could say G1 to F3. Let's see if that's right. And our board updates, boom, our knight is up here. And so now that we've done that additional move, let's look at our fen again. So honestly, I won't even try to read this. You can technically see that the capital N, that white knight, is now a little bit further up. Okay, that's cool. But you can also see that now it's black's turn. There's a B there. And, oh, that's interesting. Our turn is still 2. I guess it's still technically round 2. I think that's actually full moves, so like everybody going once. So maybe we can check that if we say push san again with a white move. So in this case, maybe we move G5 to G4 to threaten the knight. So if we say G5 to G4 and look at our resulting board. Oh, I'm really good at spelling. Board, push san. G5. Wait, G5 to G4 is not a valid move? Let's see. If somebody sees why G5 to G4 is not a legal move, let me know. Well, let's debug this. Let's look at our legal moves. Let's see. Board, legal moves. Let's see. Do we have... Oh, wait, are these... Oh, interesting. Legal moves. Okay, I don't want to get us derailed by hunting down this one particular issue, but it looks like some of these are white moves. Let's see. What if we just play one of these legal moves? What if we say B3? Because, yeah, B3 would be... Oh, I guess that'd be moving our queen out. It would be white moving the queen out. Okay, let's... Wait, no, that's not true. Is this the same board? Oh, okay. It did work, actually. We did actually successfully push it down. Oh, I guess it must have run twice, and so it went back to... All right. Yeah, so we actually did push the right piece, and we can see that moved down. And so now if we look at our fen again... Yeah, apologies for the confusion there. If we look at our fen again, okay, now it is turn 3. So we both made 2 turns, and so now it's our 3rd turn. But we debugged it. Yeah, it did just make the move and then try to make it again incorrectly. Okay, right on. So that is part 1. That is understanding Python chess, our little library for interacting with a chessboard, and an FEN, Forsyth Edwards notation. If you have any questions about either of those things at this point, of course, let me know in the comments. Otherwise, we will jump ahead to part 2 and actually try to start building a model that will play some chess for us. And I will stall for just a second and take some water in case anybody has questions. Stay hydrated, friends. Okay. So let's jump back to our competition here. We can go back to code. I'll just keep dropping the links just in case they're helpful. And we can come down to part 2, building a simple chess playing model. And again, I will click edit here so we can play along. Okay, so as we talked about before, in order to actually build a model that can play chess, we need to write a function that accepts a board state specified as an FEN or a FEN and returns a move. specified in that standard algebraic notation where it's like G1 to F3 or something like that. We can use Python chess to generate a list of all legal moves. So a super dumb way, this is not technically actually an AI, but a very dumb way to do this would be, say, get the list of legal moves and randomly pick a move, right? So we can go through and actually code this up, and we can say pip install Python chess. Here, let's run this guy. This is something I go back and forth on. Should I code it up live, or should I just show you the code that I wrote while researching? So let me know if you have feelings about no, Will, I want to see you live code it. That's more engaging. Or feel free to let me know that this works just fine. We end up going, I think, a lot faster, and so I worry about losing folks if we are, just sort of zooming through code that we've already written. But we play around. We update. Let's see, DWL code gray. This is fine. I appreciate the feedback, friendo. That is great to hear. Boom. Okay, so let's talk through what we're doing here. So we're importing random. So this is just a Python library that lets us randomly pick things. You can randomly generate numbers. Ezriela, I appreciate the feedback as well. This is great to hear. Lovely, lovely. So random just lets us make random decisions like picking random moves or generating random numbers. Chess is, again, our Python chess library that we just installed. And now we're going to create a function in Python. So I don't think we've written a function in Python yet in this particular Global Hack Week. So you can use the def keyword to say I'm starting a function. Then you write the name of your function. So this is just going to be our play a random move function. Then we will put in our fen, which is that same string that we looked at when Pooja. I appreciate that as well. This is great to hear. And then we can, inside our function, create a chessboard from that fen. So instead of just creating an empty chessboard, so if you say, just to demonstrate this, if you have just an empty board, it'll just start like this. But say we have, we create a board and then we say board push san, let's see, F2 to F4. We've made a move. And now if we store the fen of this, so we could say one move in fen. We can see what that fen looks like. And if we want to recreate this board later, we can say chess.board fen equals whatever fen we saved. So we can kind of recreate a game just from that one string, which is super helpful. So we are sort of recreating a chessboard from our fen string. And then we're getting our list of legal moves, turning it into a list, and then just picking something at random. So we've stored a move, and then technically this move, it's like a special move object that has a lot of information about it, but we can just turn it into a string to get that very standard, C4 to F3 or whatever, that standard, or that long algebraic notation. So I think we already ran this. And so just to test it out, let's create a board equals chess.board. And then let's say we can get the board fen, board.fen. And then let's just say play random and pass in our board fen. We get A2 to A3. So that would say move. I guess we can actually see our board. So this is our fresh board. So A2 to A3 just means go this pawn from A2 to A3. And if you've played chess before, if you're kind of good at it, you might know that this is like a pretty bad move, right? There are a lot of good reasons. Like in general, you want to get your pawns out a little bit further into the middle of the board. Usually, you don't want to move the pawns at the very ends of the board. You really often want to advance these pawns in the middle because controlling the middle of the board is a really nice chess strategy. So that's like a pretty bad move. But we could take that bad random move and we could just plug it back into the board. So we could say push san, whatever comes out of play random, right? And now if we look at the board, it'll be a different move. Okay, it made a slightly better move this time, right? And we could even do this in a loop, right? We could keep looping and keep playing random moves. And in this way, we could actually play against our little basic model, right? So I will clear this out. We'll delete some cells. Boom. Right on. I went ahead and wrote this code to actually let us play against a model. Let's walk through it. So this just lets us print out our board. It's really easy to see your board as a picture if you just leave it at the bottom of the cell. But because this is going to be a loop, we actually need to like do some special work to make our board come out as an image. So we just have this function called play game, and we're going to give into this function whatever AI function, whatever our AI is doing, right? So our function up here, like play random, we can pass that in as this is how the AI makes decisions. And by default, we're just going to say the user will always play as white and will always have the AI play as black. That'll just make things a little bit simpler. So we'll start our game by creating an empty chessboard, and we'll enter into this while loop. Y'all, this is Global Hack Week Games. We're coding up a little game loop. Isn't this fun? I feel like it's funny because this is probably, of all of like the game adjacent streams, I just have like, I am not really not a game developer, right? Like I've played around with Pygame, but like I don't know the first thing about Unity. I am not, but we're out here in machine learning world coding up a game loop, or an event loop. So as long as there is no outcome, as long as the game hasn't actually finished, we will keep this loop going. And we'll start by printing out what our board looks like. And then basically we'll do two different things depending on whose turn it is. So our board actually keeps track of whose turn it is. And so if we say, if the board says it's white's turn, then we will let the user make a move. So we'll start by prompting that user for some input. And if the user types out quit, we'll just let them get out of there. But if it's not quit, we will actually try to see if their move is a legal move. So we'll enter into this we'll do this check that says if the user move, like whatever we entered in our little text box, is not inside our list of legal moves. This is just it's a list comprehension, turning all of our legal moves into strings. So basically, if the move the user said isn't somewhere in our list of legal moves, then let's just reprompt them to enter in a different move. I've done this a lot. Doing the long algebraic notation, it is a little bit of a hassle, and so this is nice, right? It'll just give us a chance to, if we make a mistake, try to figure out what our issue was. And then once they make a legal move, then we actually make that user's move. And if it's white's turn, then we'll just skip back and we'll come around and it'll now be black's turn, right? If it's black's turn, however, we will just say the AI move is whatever the AI function says. So we feed in the current state of the board as this fen string, and then we let the AI function return to us whatever the move should be, and we'll actually print out what the AI move is, and then also just execute that move on the board. And then if we do this long enough and somebody wins, either from a checkmate or a stalemate or a draw, then board outcome will be something, and we will actually print it out. So we write this function called play game, and just by calling play game with our play random function, this will actually let us play against our sort of random AI. Again, AI in air quotes. It's not actually an AI. It is just picking random moves. But let's see if we are good enough to actually beat it. Let's see. If folks want to, we can do this sort of like live stream chess playing where people comment in the move that I should make and I will make it. Or you could just give me advice. But I'm a very basic chess player. If I'm playing as white, I am almost always doing e2 to e4, which is I don't know, maybe not that great of a move, but let's do it. Let's open with e2 to e4. So things went really fast. I did e2 to e4. Then we can see the AI move. So this is after just my move. I moved my pawn up. And then the AI move, b7 to b6, moves their pawn down. Okay, cool. So I have this advantage that I know the AI is playing randomly. And so I can just like try to be horrendous and mess things up for it. But so like, I think I actually have the ability to, over the next 2 turns, move my queen out and then take black's rook if I get this pawn out of the way. So why don't we do that? Let's move our pawn up so we can move our queen out and then maybe take their rook. So we could say e4 is this pawn, and we just want to move it to e5. So we can say to e5. And okay, cool. So our pawn moved up, and the AI move was to move their pawn from A7 down to A6? Yes, Mr. Mustard. Excellent question. Our AI is not doing anything special here. Our AI is just picking random moves, right? This is just kind of to see, okay, can we play a game against an AI? Does it kind of work, But then we'll actually set to work actually trying to make the AI smart, which turns out it takes a lot of pre-processing code just to get things into a good state. But we will get there. Okay, so now I think I have a chance to, if the random player doesn't move their rook, then I could maybe move my queen from D1 over to F3. So I'll say D1 to F3, and then I should be able to take their rook on the next time. Let's see. Yeah, to be clear, like if I was, this is not how I would play if I thought the AI was actually going to, to make good moves. Okay, cool. So we moved our queen up, and we're now threatening their rook. And yeah, they don't even see it because they're picking random moves, and they move their pawn from F7 down to F5. And so now we can see what it looks like to actually do a take, and we can say, let's see, queen from F3 over to A8. Boom, and we took a rook. So we are now up 5 points of material. This is a detail we'll talk about later. In chess, we count the total number of points on the board as points of material or pieces of material. And so the pawns are all worth 1 point. The knights and the bishops are worth 3. Rooks are worth 5. Queens are worth 9. And kings are kind of worth like infinity and 0. Let's see. Tomwell said, how does it handle illegal moves? I think I missed it. Oh yeah. So we just check to make sure that whatever move you do fits within the set of legal moves. So like I could say, if I want to move, it'd be like really great to have like my king teleport and jump on their king. So I could say E1 to E8. If that worked, that would be super dope. But yeah, not a valid move. Please enter a move in standard algebraic notation. And also, I think a thing, I already blundered my queen to the random AI. That's really, really funny. That's you're hanging out with me over here at ELO of like 7 club. For the record, I don't know how much folks are into chess, but in the announcement for this, I mentioned I have an ELO of 7. That's not actually true. I don't know what my ELO is, but ELO is like generally people start at like 1500, and like 500 is very, very bad. So saying you have an ELO of 7 is kind of a joke. Okay, but something that is actually fun is because it's limited to only playing legal moves. Then if there's only one move, if I've put it into check and there's only one legal move for it to make, it'll have to make that move. So we could actually do this by getting our queen in to threaten the king, and it'll probably be forced to take our queen. So let's just try to keep moving our queen across the board. We can say A8 to B8 and take the knight. We took the knight, and they did some other random move. We could say B8 to C8 and take their bishop. And yeah, of course, they didn't even take our queen, even though we're threatening their queen. And so now we can do the final thing and do C8 to D8. But now something's going to happen where we have put their king into check, and they only have, I think, 2 legal moves, right? So once I'll make this move. So I moved here, and you can see it's red because we put the king into check. And so this means the king only has 2 legal moves. It can either take our queen or it can move up here. And because it's moving randomly, it does really the bad option of moving the king up here. But hey, we can keep going. We can force it into something. If we go from D8 to F8, I think that should force it to take our queen. Okay, cool. So one legal move after we moved our queen over here is that they can take our queen with the rook. So there's our little game loop. We're playing some chess against a computer. I really wouldn't call it AI at this point. We can click clear outputs just to get rid of all of that. Let's scroll way up. We're skipping ahead. Cool. So that's fun. We want to level up our game, right? And there are generally 2 ways that we can talk about building a model, and they come from the world of reinforcement learning. I often sort of, when I do these these live streams, I will talk about how, yeah, you have supervised learning and you have unsupervised learning and you have reinforcement learning. So supervised learning is when you have sort of labeled examples, right? Like you give your model a bunch of pictures of cats and pictures of dogs, and you say, hey, like learn what makes it a cat, learn what makes it a dog, and later I'll ask you, is this a cat or a dog, right? Unsupervised learning is sort of trying to learn some structure inherent in the data. So the classic example we have is you have a bunch of customers in your database and you want to cluster them into groups, right? So a clustering algorithm is a form of unsupervised learning. And then I always sort of gesture at, and yeah, then there's reinforcement learning. It's like kind of whatever. Excuse me. But we won't actually really be doing much reinforcement learning today, but we will be borrowing ideas from reinforcement learning. So reinforcement learning is when you can actually put your agent or your model in an environment. So games are a classic example of this, where what does it mean to play chess well? Well, we kind of know. It just means that you win games, right? And so we could put a reinforcement agent in a game and basically say, keep trying things until you figure out something that works, right? And it can sort of generate its own labeled data by playing it out. So there are these two ideas that we'll borrow from reinforcement learning called policies and value functions. So reinforcement learning, a policy is just the fancy word for a function that goes from whatever world state your agent is in. So there's like everything that your little model knows about. It goes from those world states to actions that your agent can take. So there's a pretty natural fit for chess, where basically our world state is what is on the board, and our actions are what are the legal moves that our AI could make, right? And so you might think, hey, what we're really looking for here is a policy. We want to generate a good policy for playing chess that goes from the board state to what the best next move is. There's one catch here. Our world state is like relatively simple. We can specify it in this fen, and it only takes, I don't know, 100, I guess 64 characters to sort of show the chessboard. But there are a lot of potential moves. In a lot of, say, video games, really your options are like move up, move down, move left, move right. Really, you have 4 options at any given point. But in chess, if you think about it, like all the possible moves, it is possible to move from any square to any other square, right? And there are 64 squares on the chessboard. And so there are 64 potential starting squares and 64 potential ending squares. You can say technically 63, but whatever. And so that's 64 to the power of 2 is 4,096 like possible moves that we could make, right? What's more is that at any given turn, most of those moves that are technically possible are actually not going to even be legal moves, right? Like I joked about if I could have my king like teleport and kill their king, that would be great. But that's not a legal move, right? So our model is going to have to try really, really hard to just figure out if a move is a legal move, because there are so many potential moves. And it's going to have to spend a lot of its sort of brain time just evaluating things that are technically illegal. So that's kind of a bummer, especially because Python chess tells us what moves are legal kind of for free. So this is where we're going to bring in this other idea called a value function. A value function just basically tells your AI how good a certain state of the world is. So, for example, a board where we have all of our pieces and our opponent only has like a king and 1 pawn, that's great for us, right? And our value function would give us a really high number. If it was reversed and we didn't have that many pieces, but our opponent had tons of pieces, our value function would give us a really low number. So instead of training the model to take in a board state and tell us what move it should do, one option, so that would be saying our model is a policy. Another option we have is to have our model basically look at all moves it could make, actually simulate out, well, what if I made that move? And then evaluate the board afterwards with a value function. So if we do it this way, all we have to actually have our model do is look at a board and tell us how good it is, right? So you look at a board and you just output a number that's high or low or something. And then just loop through all the possible moves your board can make. And then pick the move that gives you the highest value function result after you make that move. So this is like the, I don't know how long I was talking there, maybe 5 minutes. This is the 5 minutes of sort of reinforcement learning theory here. We talked about policies and value functions. But I want to pause for a beat and see if there are any questions about this, because we're getting a little heady. We could maybe do a quick recap. A policy is just something that goes from world states to actions. So this would be saying a policy would be look at a board and say what move you should make. But a value function is just a function that takes in a world state, so takes in the board, and just tells you how good it is. So the kind of thing it has to spit out is just a lot simpler. It's just a number of is it good or bad. And we can use our value function to evaluate all the possible moves we can make and pick whichever move gives us the highest value. We feeling good about this? Okay, right on. Also, I want to say before we get deep into this sort of coding up an AI model as a value function, is you could actually code this up as a policy, right? You could say, hey, my model takes in a board state, and it does spit out one of 4,000 different moves. And I'd actually be super interested to see if someone codes that up, how well it does. I mean, Mr. Mustard, I appreciate the reality check that I'm not speaking to the void here. Incredible. Okay. So now we are going to get, if you've done much machine learning, there's this joke that like 80% of machine learning is just cleaning your data. And I promise it won't be 80% of the time we spend, but we certainly are going to spend a decent chunk of time thinking about how to turn our board into a good representation for our model. So we start with our board that is basically this 8x8 grid of characters, right? We've seen this before. We know that we can turn our Fen notation into a board that looks like this, right? But notably, our model doesn't intuitively know what an R means here. It doesn't know what a P or a Q or a K means. And one really common method that we'll use in machine learning, from going to words or characters to numbers, is called one-hot encoding. So right now, there are 13 different characters on the board, right? There are 6 different lowercase characters, 6 different uppercase characters, and periods. So instead of just including the characters, we can include a list where there is a spot in the list for each individual type, and only put a 1 where the specific type is. And this feels a little bit heady. If we were to one-hot encode a white bishop, so a white bishop is this capital B, we can imagine coming up with a list that is 13 things long, and we can say there's a 1 for the bishop and there are 0s for everything else. So this can often just be a simpler way for our model to really understand what something is, because here it understands it's not a white queen, it's not a black rook, it is a white bishop. And that is where our 1 goes to one-hot encode. Let's see, Mr. Mustard said, for chess specifically, how would each piece on the board have a value function associated with it? Like a number describing how good a position it's in? Okay, so this is a great question. So one way you could think about this, like one really simple value function. So I want a table of one-hot encoding so I can answer this question, but try to dive into if one-hot encoding makes sense. But so one really simple value function that we could write is just this idea of points of material, right? So we said, a pawn is worth 1, a bishop is worth 3, a queen is worth 9, and we could just basically add up all of our points of material and then subtract our opponent's points of material, and that will give us a number. And that's like a very simple value function. Oh, me, Mr. Mustard, do not apologize. I love it. Honestly, all I come to Global Hack Week for is to go on tangents. That's what I'm here for. So a very simple value function would just be to add up the points of material, right? And this would be like a pretty simple one where you take in the whole board and you basically say, yeah, like having a rook is worth 3. Sorry, having a rook is worth 5, and so you add up 5 for every rook, and you do this math. But as you pointed out, there is like this idea of we have good positions and bad positions, and like we have even positions where where your rook might be worth something, but if I have a bishop threatening your rook, that's worth a little bit less, right? So the big idea here is that we could build a really simple value function that didn't really consider how things interact. But the one that we're going to be building is going to be a lot more complex and be able to consider these things like, well, hey, your rook might be worth 5 points of material, but if your rook is stuck somewhere and about to get killed, like it's not actually worth that much to you, right? But so the value function will take the whole board at a time and spit out one number. So it kind of summarizes how good the whole board is. Hopefully that answers the question. Right on. So this is our one-hot encoding for a white bishop. It's all zeros except for this spot. And then this is how we would encode a space, right? So we have all zeros and then a 1 right at the end there. Those in both examples we have 1 1. First I was reading this, it says 11. But we have 1 1 and the rest are all zeros, right? So this is called one-hot encoding. Only one of our spots in our list is hot. Let's see, Wigan Inc. says how to implement value score for moves. Yeah, so this is another good question. So we have this value function that tells us how good the board is. And so one simple way that we can evaluate moves is basically just try out all of our legal moves. So try this move and see how good the board is afterwards, and then try a different move and see how good the board is afterwards, and basically simulate out all our possible moves and see which move gives us the best looking board afterwards. And so we'll look at this in a second after we actually code up sort of our core model. We'll be able to actually put it in this sort of loop and play around with it. So the first thing we have to do is code up a function to do this one-hot encoding. So we are importing NumPy. NumPy is just a fun little utility that does math and matrices for us. So we can define a function called one-hot encode piece, and it takes in a piece. It's a character, and we basically have a list of all of our pieces. So these are all the possible letters we could have. Then we can make a np.zeros just creates an array of all zeros of a given size. So we could just pull this out and actually show you what this looks like. So if we just actually, let's just start with pieces. This creates just a list of all of our pieces. I was thinking about it. Are we still? Okay. We're actually still playing our game, aren't we? Okay. So you can click this pause button on there to stop a game. And now we can run this. So we get a list just with all of our individual characters, and then we can get an array that is the length of how many pieces we have, but just zeros. Now we have to import NumPy. Import NumPy as np. So we just have a list of, in this case, 13 zeros. So then we can create a piece to index. So basically all this does is we're just going to create basically saying each piece gets a special number. So if we create this piece to index, we can see, okay, we're just saying lowercase rook is 0, lowercase knight is 1, lowercase bishop is 2, and so on and so forth, and a period or a space is 12. And so then we can just turn our individual pieces into indexes, and whatever that index is, at that spot in our array, we'll set it to a 1. So like, for example, if we go piece to index, and we have lowercase b for bishop, we'll get a 2. So we could say our index is 2. And then if we take our array, and we basically take the bishop index and say you are now equal to 1, if we look at what's inside our array, we'll see it'll be 0, 0, 1, because we start counting from 0, and our number 2 index is a 1. So we've just one-hot encoded a b into this one-hot encoded array. We're now really getting into the, we have arrays, we have matrices, we're doing one-hot encoding. This is real machine learning stuff. So if we have any questions about this, if you're confused as how we got this array, then let me know. Also, if you just want to say, hey, we're getting into some messy data stuff, I'm going to mentally just kind of hang out and follow along. That's totally cool. You actually, I would recommend that you get deep in on this, but you absolutely do not have to in order to actually understand how this thing works. Or to actually mess around with our machine learning models later, I should say. So if we stitch that all together into a function, we get the same output here. We one-hot encode lowercase b, and we get this output. If we did an uppercase q, we get a different output. Now the 1 is over here. So these just all uniquely represent pieces. Okay, so now we want to encode our entire board. I'll take a beat and take a sip of water. If anybody has any questions about our one hot encode piece function, let me know. Right on. Cool. Encode board. So we've encoded each individual piece, but now in order to give a really nice summary of what our board looks like, we want to encode pieces for every piece in our entire board. So the first thing we'll do, so encode board will take a whole board fen string and turn it into, it'll take a board like a chessboard, a Python chessboard, and it will first turn it into a string and then turn that into a giant matrix for us. So let's walk through this. So turning our board into a string, remember this just gives us that nice little, let's see, let's look at board string. It gives us that nice little, actually let's do board chess.board. Good. Okay, yeah, this is good. We're going to print it out so it renders the new lines. This gives us this cute little board right here. So we have our letters and we have periods for spaces. That's really convenient for us. We can then say replace all our spaces with nothing. So this will effectively get rid of all of the spaces. And so we print this out. Now it's just condensed and there are no spaces. A little bit less nice to look at, but it'll be easier for sort of programming with. And so then we're going to create this list of all of the things that we've encoded. And so we can split our board on the new lines and go through each row in our board and take each cell in our row, so each piece in our row, and one hot encode that piece. So just to walk through this, we can turn our board into a string and then replace the spaces in that board with nothing. So we're just deleting all of our spaces. And then when we split on new lines, let's just print out each individual row. So we're getting kind of the whole thing. But inside each row, if we wanted to, we could print bloop, just so you can see. Okay, we print the first row, and then we say bloop. And then we print the second row, and then we say bloop. So we're just looking row by row. And then inside of here, we're iterating through each piece in our row. We could even just print out piece. So at this point, this is still just a letter, right? We're going through and looking at all the individual pieces represented by their letters. But now we can just encode this piece if we want. And this will suddenly get very big. What do we say? Encode, one hot encode piece. That's what it's called. So we're just, for every item in here, we're giving it an encoding. And we can actually look at this and kind of make sense of it if we try. It's a little bit of a mess. But so remember, our first thing is a black bishop. And okay, yeah, the one space is a black bishop. That's the first cell in the first row, right? Or the first piece in the first row. And then our second spot is a knight, and that is what is right next to the bishop. Sorry, not bishop, rook. Our one is a rook, isn't it? I misspoke. And you can go through, and this actually technically shows you the entire board. There are 65 of these cells. So we can delete this cell. We don't need any more. But if we put that all together, we create this whole board list of all of the individual pieces in this one hot encoding way. And then we can turn that into an array at the very end. So if we put this together and we just look at our basic chessboard from the starting position, this is what our output looks like. And obviously, like to you and me, this just looks very like how is this nice? What have we accomplished here? But trust when I say that this is like a perfect representation to feed to our AI model. So this is a little bit like this is kind of dating me because this is an old movie when I watched it. But if you have seen any of the Matrix movies, I've only seen the first one. But there's that scene where someone's staring at like a screen of ones and zeros, and they're like, "I see everything," and like they can really understand what's going on. And that is kind of what we're doing here. We're doing the Matrix moment with the AI, giving it all the ones and zeros, and it can see everything. Drop in the chat if you are even familiar with the Matrix franchise, because I don't know, it was not a movie that I saw until relatively recently. But if you want to make me feel old, go ahead. Right on. So we have encoded our whole board into this giant set of zeros and ones. Let me know if at this point, if you have any questions about encode board, then let me know, and we can unpack them. Me and Mr. Mustard saw the first one years ago. Okay, boom. I thought it was a nice movie. I thought it was fun. That movie actually has like some takes on the AI taking over. That one's fun. Okay, cool. So we have done all of our sort of grunt prep work here to get our board into this really nice format for our AI, and now we can actually get into it. Now we can actually start building up a set to play with actual models. Your patience will be well rewarded. Earlier we were looking at our training data, and in fact, maybe we'll jump back to, let's see, where is our actual competition? Oh, I guess we can just come over here. We can click this button. And if we go back to data, in fact, it's been long enough that I'll drop another link here. Boom. If we come back to data, we can click on our training set right here. And we can see we have a couple columns. We have this random ID. We have our board, which by now we know exactly what this means. We've seen this. We've been around the block. We have a black score, which this is basically what we want our value function to output. This is, a board that's really good for black will have a really high number here, and a board that's really bad for black will have a really low number. And then we have our best move as told to us by Stockfish, right? So if we come back to part 2, we can use pandas is just a cute little library for basically importing CSVs and treating them like spreadsheets. So we can actually play around with that a little bit. And if you come over here and you click here, you can see our input right here. So you can even just copy the file path. And so that's actually how we got this file path here. You paste it, and that's where our training data is. And so if we paste this and we just say train df, so df stands for data frame. That's sort of the format of our little spreadsheet. We say train df, we get all that data in our code here. So we have our board, we have the black score, we have our best move, right? So we can import that. And then the first thing that we're going to do is we're actually going to split our data set up. So there's this thing in machine learning where we want our model to do good on data it hasn't seen before. So we're going to train it on some data that we have. But ideally, we don't only want it to play well in games it's already seen before. We want it to be able to play well in any game. And so the way that we test this is we keep a little bit of our data secret, and we can use that basically as a test set. The analogy that I use here a lot is this is sort of like the training set is sort of like the study guide that a teacher gives you, and our validation DF. That's sort of our quiz that we're going to give our model at the end of it all. So we have a study guide that it gets to look at the answers to, and then we'll give it a quiz that it doesn't actually see the answers to. So we can, just like a list, we can chop this up and say our first 10,000 examples. I think you have like 80,000 examples in here. So our first 10,000 examples we'll put in our training DF. And then the other, this is no good. We have to do validation first. And then our other, like 1,000 from the end, so the last 1,000 examples we'll use for our quiz. So we can run this, and boom, our training DF looks like this. So now we have already done most of our pre-processing. We've written these really nice functions, but we'll do one more function that just goes to encode a Venn string. Because our original input expects a Python chessboard, writing this this function encode Venn string lets us take in a Venn string, so just basically this thing in the column right here, turn it into a chessboard, and then encode that board. So we could just test this out if we wanted to. We could say encode Venn string, and we could just run it on. I could just literally copy this out, and it would encode it for us. Boom. So we're going from this column of board states in Venn strings out to this giant ones and zeros thing that we're going to feed to our model. Delete that cell. So now we are going to use this functionality called apply to our board. So you can use, you can treat a data frame kind of like a dictionary. So if we have our train df, we can say train df, and then in these square brackets, just say board. And this will get us just the board state. So it'll get rid of the other stuff. It keeps the ID, because that can be often important, but it mostly just gets us our boards. And then we can say dot apply, and basically run whatever function we want on each individual row of our data set. So if we run this, we're going to be basically turning all of our then strings into that giant ones and zeros format. And stacking basically just squishes all of our individual arrays into one giant big blob of memory. And that's what we'll call xtrain. So that is our training data that goes into the model. And then our y is going to be, so x and y are sort of our inputs and our outputs, right? So our output that we're calling ytrain is just going to be the score that black gets. And this is, again, think of this as like an expert coming in and just looking at a chessboard and saying, yep, this is a really good position for black, or this is a really bad position for black. And we'll do just the exact same thing to our validation data. And remember, this is sort of like the data we don't let the AI see the answers to, so we can quiz it on stuff it hasn't seen before. So we can run that, and that'll take a second because we're doing a lot of data churn. And if we just look at our xtrain, you can see it's all this format of the ones and zeros, right? So now we get to come to the fun part, right? Now this is like actually the let's just throw some stuff at the wall and see what kind of performance we can get. So purposefully, this is a really, really simple setup. But it is like a good starting point to sort of build off of and to experiment with and play with, right? So there is a library called TensorFlow, which is this great library for building machine learning models. It does a lot of sort of like the underlying math for you, and it gives you these sort of Legos that you can put together to build your own AI models, your own machine learning models. Interestingly, this is something that historically for Global Hack Week, I've done stuff with TensorFlow, and Keras is sort of like this nice little library that sits on top. There's also this big library called PyTorch, and recently I've been getting into PyTorch. PyTorch is used a little bit more in like the research community, and TensorFlow I think is used a little bit more in the sort of like industry. They're both used all over the place. PyTorch has been growing a lot recently, and I've been learning PyTorch. And I started implementing this in PyTorch, and I realized it was just like 100 more lines of code, and so I decided to not put you through that. But PyTorch is really cool. It just can be a little bit harder to get off the ground sometimes. So TensorFlow is this library that gives us all of these guts, all these little Lego parts to put together our AI model. So a sequential model is like this overarching architecture that basically just says data comes in your model on this side, and it goes in this sequence of different layers, these different Legos that we stuck on top of each other, and then it spits something out at the end. And so we're taking in our data that we've just prepared so nicely, doing a lot of processing to it, and then spitting out a rating of how good the board is. Ezriela, I hope that the oh no is just on PyTorch being complex and not some other reason. So we can create a sequential model and then pass it a list of all the Lego pieces we want to put in there. And this really simple model, we're only going to use 2 kinds of layers. There are like 100 different kinds of layers you can put in there. Yeah, PyTorch is really great, and if you want to go deep on learning how to build your own sort of like novel tensor functions, like PyTorch could be incredible, but it could be a little bit daunting. And Keras is just really easy to get started with. So we're going to have two layers here. One is called a flatten layer. So remember our original encoding that we came up with? It is technically a 3-dimensional matrix. So we have our board already is two-dimensional matrix, right? We have our 2 sides of the board, but then we also have this 3rd dimension now of what piece is on the board, right? So we technically have a 3-dimensional matrix, and one thing we can do just to make our life simpler is just say squish that all down to a single line of numbers, and that'll be a really, really large line of numbers, but just squish it all down, right? So then our next layer is going to be a dense layer. And a dense layer is sort of the bread and butter of most machine learning models. It basically gives you a little bundle of artificial neurons that are all plugged together. All the neurons talk to everyone else. I wonder if we can find a good picture of like a visualization of a dense neural network. Try to introduce some good images. Okay, yeah, like these are fine. This is a little bit mathy, but like this right here is a dense neural network layer where all of the things on this side connect to everything on that side. And this is the same. So all of these are dense neural layers. So that's what we're plugging in here. It's sort of the simplest thing. Sometimes it's not the best, but often you can get sort of decent performance with a dense neural network. And then an activation function. We're not going to go deep on activation functions, but this is basically, if you are, it sort of comes from the idea of a neuron. If you're familiar with sort of basic neurology, you have a bunch of inputs coming in your dendrites, and then your neuron has some action potential that it has to decide if it's going to fire or not, right? And so the activation function here basically controls how it decides if that neuron fires. And so there are lots of different functions people will use for, oh, maybe it should fire, just a little bit if it has a little bit of input and a lot if it has a lot of input. Or maybe it should just kind of be on or off, just sort of a binary thing. So ReLU is one potential function. And then our final layer is actually really important here. Our final layer, we have a 1 in there, specifically because we only want to put out one number, right? The thing we're predicting is just a single number of how good is this board state, right? And so our dense neural network here is going to output one number. This also means that in our dense one, we are creating 128 sort of little neurons on the inside. And so this is like a number that you can play around with. In fact, already, I think this is a very simple model that I would say go ham on playing around with this to see if you can get better performance. Try adding more layers. Try adding more neurons per layer. But the things you're going to want to keep this because this says, let's just flatten our input. And then you're going to want to keep this because it says output one number. And then feel free to add more of these or change the number. So that's basically saying how deep is our neural network, how wide is our neural network is, you can imagine adding more of these. Then we have to do something called compiling our model that tells it basically how it's going to train. So RMS prop is super interesting, but it is a way of basically how does our model learn from feedback. So our model has all these neurons, and it's going to sometimes get things right and sometimes get things wrong. And our optimizer basically says, when you get things right, what should you do? When you get things wrong, what should you do? And then finally, our loss function here basically says what is bad. And so this actually is a great connection to the question that Wigan Inc. just asked, is the loss function basically tells the model what we want it to achieve. And right now, to be clear, all we're actually asking our model to do is to correctly predict how good a board is. So if a board has, a bunch of queens on it, we'd like it to give that a high number, or a bunch of queens that belong to us, we'd like to give that a high number. And if it has, if we only have a king left and they have a bunch of pieces, we'd like that to give it a low number. And so this loss just basically says, you want your number that you spit out to be close to the real number that we've already logged. Hopefully that feels okay. So we can run that. And then this is where things get exciting. And we can actually run our training process. So we put in our training data, X and Y. We tell it how many loops it should run for. So an epoch is just how much it looks at all the data. And then our validation data, given X validation and Y validation, is basically when we give it its quiz, when we see, hey, how good did you do? And so if we run this, we'll be off to the races. It'll take a second, but it'll get going. And then this history variable here basically just says, let's capture everything that happens. Now, these two columns, I think, are super, super fun and interesting because our loss is going down. So this is some really high number of how far away it usually is from the right answer. And our training loss and our validation loss both start high. And then over time, as it trains, they both get lower. And you can see that our training loss seems to get lower a little bit faster, but our validation loss still keeps going down. So it's getting better at evaluating boards it has seen, but it's also getting better at evaluating boards it hasn't seen yet. And this is really important if we want it to generalize. Yeah, I think it's really cool too. This is always a fun moment. We've done all of sort of the grunt work, and you get to see like, oh, it's improving. So now, after we've trained our model, I want to use that history that we have to actually look at what our loss looks like. So our loss is basically how bad did our model do, and we'd like it to do less bad over time, right? So if we run this, we can see some graphs. Now, if you have ever looked at these kinds of graphs, these training graphs, you will know this is actually beautiful. This is great. We love this. So we see that basically the whole time, both of our lines are going down. In fact, you could say this actually means we could probably have trained for a lot longer. We haven't even, you can see at first we're improving a lot really fast, but we could even try longer, and we'd still make a little bit more progress. So this is, we're now like in the mode of, oh, we're doing machine learning science. We're playing around, we're seeing how we get better results. So one thing that we could come up and do is we could say, hey, what about not for 20 epochs? What if we went for 50 epochs? And that'll take longer, but maybe we'll get a better result. So we can run that. Hey, thank you so much. I'm so glad that you're enjoying and you're getting something out of it. This is, a thing that I have been playing around with for, machine learning in general for, almost a decade now. But every time I get the model to the point where I can actually let it train, that's always still a lot of fun. So you can see our numbers keep getting lower. And the lower these numbers are, the better our model is at telling us how good or bad a board state is. So you can see now it's taking real time, right? And this is even like a laughably small model, but it's still taking time. And it's still improving. It'll be interesting to see what our graph looks like after this. So usually in machine learning, you hit a couple of points. One is a point where it's called convergence, which is basically you could train for longer and your model just wouldn't do any better, right? There's also a thing called overfitting, which is basically the example I use is, okay, our training data set is sort of our study guide and our quiz is our validation set. And something that can happen is a really, really smart but devious student can just memorize all the questions from the study guide. And when it goes to take the quiz, it won't actually do that well because it just memorized a lot of answers. It didn't actually learn the content. And so how we would see this is if our training loss was really low, but our validation loss actually went up. So you did really, really good at memorizing the data, the study guide, and you did really bad at taking the quiz. So let's rerun this graph and see what we got. Okay, so this is cool. So you can see we're still improving. Things are still getting better, but we're kind of leveling off a little bit. And notably, our validation loss is leveling off even more. But I won't spend too much longer on this because this is something that you can play around with and see if you can get better results. But our training progress looks good. So this is now a value function. This takes in a board and it tells us how good or bad that board is for us, right? Notably, it actually, because the thing it's predicting is the black score, it's telling us how good or bad the board is for black. So we can take this value function and basically run it on all of our potential moves and turn that into a policy. Because Python chess already gives us all the legal moves we can make, we can just take a look at those legal moves and see if I make this move, how good is it, right? Oh, Ezreal, I'm so glad this is working for you. I always have a blast talking about machine learning, so it's great to have you all here. Right on. So we'll define this function called play neural network. So our first function was called play random, and this one will be called play neural network or play NN. And so we'll take in our string, that's our fen string, right? We'll create a board from it. And now we'll get two lists. We have all the possible moves we can make, and then we have our input vectors. So that is for all the possible moves we can make, basically playing that move and then turning that into that giant ones and zeros thing that we brought up in order to feed it to our neural network. So we can say for all of our moves in legal moves, we can create a copy of our board. This is important because we want to actually see what happens in one scenario without actually committing to it. So for our first legal move, we'll create a copy and push our move, and then add that move to our list of moves, and then add the vector of that new board to our list of vectors. So this takes we'll say, well, what does the world look like if I made that move? And then this line just encodes that board and then flattens it and turns that into, adds that to our list. So we have a list of basically all of what the boards would look like in our AI-friendly format if we made a particular move. This just stacks all of our input vectors together, so we get one giant chunk of different possible boards. And then we ask our model to predict. I have verbose equals 0 just so it doesn't actually spit out a bunch of logs. But it's going to give us a list of scores back. So let's actually, before we actually try this, let's just print out scores. Let's print out moves and print out scores. Moves and scores. And then we can just return so we don't run into the rest of our function. So let's run this and then call this on. We can do chess.board.fen. So this is just running it on the starting board. If we run this, we'll get, okay, we have our list of moves. These are all the possible moves we could make. And then they have a list of scores. So G1 to H3, that would be, I guess, moving our knight in the bottom right corner, sort of out to the side. That gets a low score. But moving G1 to F3, G1 to H3 moves the knight sort of towards the center of the board. And then G1 to F3 moves it towards the outside of the board. And so we can see that second move gets actually a really negative number. And this actually, if you know some things about chess, this actually kind of makes sense. Like usually we want to move our pieces closer to the center of the board so we sort of control more space. So like already that kind of makes a little bit of sense. So we get a worse number for a move that we think would be worse. Hopefully that makes some sense. All right, I'll delete these things we just added. So now we have to get a little bit positional, because really we want this function to work both for playing as white and for playing as black. And that function, what it just gave us was, technically it gave us scores for black. So everything I just said was technically reversed. Apologies for that. But so if it's black's turn, we want to find whatever move had the highest number. And argmax is basically it is a function that gives you the index of the highest number in a list. So I just want to show you what argmax looks like. So we say np argmax. If we have a list of 1, 2, and 3, because the indices are 0, 1, and 2, or here, I'll make this even easier. We'll just say 0, 1, 2, 3. The highest number is that last one, at index number 3. And so np argmax should give us 3. Boom. So it tells you where the highest number is. And if we move 3 and 1, it should now give us the number 1, because our highest number is at spot 1. So this is just a way, argmax is just a way of finding where the highest number is. And if we're black, we want to find the highest number, right? But if we're playing as white, we actually want to find the lowest number, because we want the board that looks the worst for black, right? And so we can actually run argmax just on the negative of all of our scores to sort of flip it around. Now this if statement here just says, if we pass in show evaluations, that like lets us see all of the moves that it made and what it thought they how good it thought they were. Then our final thing we'll have to do before returning the move is just take that index of the best move. So we did argmax to say, give me the label or the index of the highest number, the highest score, and then let's take that index and find what move that corresponded to. And that should give us our best move. That is a lot. That's like a big chunk of stuff there. Let's see. Hermiodor, correct me if I'm pronouncing that correctly. Hermiodor, is there a difference between argmax negative scores and argmin scores? Oh, this is a great question. I don't think there is actually. I think doing the negative sign is kind of fun. But yeah, it should be actually exactly the same. So argmax, if we did, let's see, we could say np array, let's see, 1, 2, 3. So this would just give us 2 because 3 is the highest one. But if we set negative np array, it gives us 0. And then if we did, instead of that, if we did argmin, it should give us the same thing. Boom, yeah. So argmin and argmax of the negative are exactly the same. Great point. So feel free to use either one here, I guess. Oh, this is, okay, that's jumping ahead. So I know this is a big chunk of code, but what we're doing here is we're going from a value function, which is just telling you how good or bad a board is, into a policy where we evaluate all the potential moves we could make, see which one looks the best after we make it, and then return that move. So something that we can do, now that we've written this function, is we could just try it on the starting board, right? So we could say chess.board. This is, of course, our starting board. And we could play neural network on, I think we pass it in the Fed, right? And this says G1 to F3. Very interesting. So G1 to F3 tells us that we should move, if we look down here, our horsey, our little knight, to F3 up here. And that is actually not a terrible starting move, right? Again, I'm not a chess expert. In fact, I'm laughably bad at chess, but that's not a terrible move, right? It seems like of all the moves you could make, that's much better than when it was moving our pawn from A2 to A3. So now if we want to, we can actually play against this AI, right? We haven't given it that much brain power. We haven't trained it that much, but we can play a game and see what happens. So why don't I actually start with what it says? So G1 to F3. And okay, so now I'm playing against an AI that, like, in theory is not super dumb. So it moved its pawn down. So now I'll move my other knight from B1 to C3 to threaten its pawn. Why not? So from B1 to C3. And it does I would say, a relatively smart thing of moving its pawn further even more. So it now threatens my knight. So now it can actually attack my knight unless I move out of the way. And okay, let's have some fun. Let's just move our knight to take the, this is not a particularly good move, but we can take their pawn and we can see if the AI takes our knight with their queen, right? If I move my knight to take their pawn, then my knight is sort of exposed and could be taken by their queen moving straight down here. So why don't we test that out and see if it catches that take? We can move from F3 to D4. And oh, it does not get it. Okay, so I would say this is a blunder on behalf of the AI, which, to be fair, it is maybe a little bit more complex. It made a couple moves that, like, seemed pretty reasonable, but, like, the decision to move your queen out in sort of this exposed place to take this knight, like, maybe that is a little bit trickier of a move. All right, let's do a few more moves and get aggressive, and then I'll show you how to actually submit to the competition and talk about. I'll reiterate the prizes that we're giving out. Prizes, air quotes. All right on. So what if, like, what would we actually do here? Oh, I don't know. Let's move. Let's get some pawns activated. What if we moved our pawn from E2 to E4? Cool. I was hoping it would take my pawn with its horsey, but because then I could take it with my knight. But that's not going to work. Let's see. Should I castle? Okay, so I can't castle yet. But if I just for fun to show castling, I could move my bishop out of the way and then I could castle. So let's say we'll move bishop from F1 to F3. F1 to D3. Actually, why not get aggressive? Let's move it from if we move it from F1 all the way over to B5, we can actually pin its knight. So we'll say B5. Cool. And so now we could castle if we want. Oh yes, well done. Great minds think alike. I trust that you didn't hear me say it and I didn't see you write it. But we converged on a great move. Okay, so now this is a little bit funky, but I can say E1 to G1, and this will actually move two pieces at once, and this is called castling. Boom, there you go. Okay, so we're playing against a model that it's clearly not. It's not destroying me. I did a few dumb things. It's not totally taking me down. But it's not making dumb moves, right? It's not being super silly. So we've taught it to do something maybe a little bit right. So it's not perfect, but it's not playing randomly either. And if we scroll all the way back up, the thing that you can play with, if you're a little bit new to machine learning and you're like, hey, I just want to play around, like see what I can do. The things that I would recommend that you play around with. One is your architecture right here, right? So like a version of this would be beefing up how many layers it has and making it bigger. One thing that actually is interesting is we talked about how there are like 4,096 potential moves. you could make one of its layers 4096 big, right? That kind of would let it consider all possible interactions getting their own neuron, right? That would make our model really big and probably slow to train, but that'd be interesting, right? So you could change that and make it a little bit beefier. And you can also play around with training it for a longer period of time, right? You can say train it for 100 epochs and see if you get better performance. And the thing to check is look at these graphs of the training loss. And if your training loss gets really low, but your validation loss stays really high, that's something to be a little bit concerned about. That might be a sign that maybe you made your model a little bit too big. Oh, the other one big thing that I'll recommend is up here, we artificially said, what if we just looked at the first 10,000 records? But you could just remove that, and then suddenly you're looking at the first, or you're looking at all the records, right? So that would just give you more training data. A few things to try. But before we sign off tonight, I want to actually get into how to submit. I have thought about it, and actually, let me know if y'all have thoughts on what we should award. But I was thinking about it, and I was thinking I'm gonna do 4 swag drops. So one of them will be if you do something interesting, you can publish your own notebook on here. So if you forked a notebook, or if you copied an edited notebook, you have the ability to also publish it and make it public. And I will go and look at all of the notebooks that get added here, and I will pick one that I think, something that I thought was interesting or one that's really well documented, and that person will get a swag drop. So 1 swag drop for a notebook. If we come over to the leaderboard, let's see. I had my boyfriend test this out. So Richard doesn't count, but also this is just the standard submission. So the leaderboard, if you make a submission, you'll be considered for a raffle. And in fact, I'll give 2 swag drops to just random people that submitted, even if you didn't get a good score. But in the highest score that is not cheating, I will also give a swag drop to. So you get a swag drop for having a cool notebook, for getting the highest score, or you could get 2 chances for getting swag drops just for submitting. And this is a little bit tricky. There's technically a public leaderboard and a private leaderboard. But let's see, where are we headed with this? So how do we submit? How do we get a chance to get a swag drop? So we'll go to part 3, which is actually making predictions and submitting. Boom. I got a bronze medal for that. Yo, y'all, upvote my notebooks. Give me bronze medals. Okay, so let's copy and edit this guy, and this will actually let us submit. So I just copied a lot of our code from part 2. We did most of the work in part 2. This is just a nice little format to submit in. So all of this code is copied from part 2, and we can just run that and get it going. So this is our play neural network function. Again, remember, you can beef this up and make this a lot bigger to show us to give us more data to train on. You can also come and make our model architecture. This is the really small model architecture, but you can make it a lot bigger if you want. And then you can also train for more epochs, right? So all of this is just running that whole bit. I just copied and pasted all that code. And then the thing that we actually want to predict on, if we go back to, let's click over here and go to our competition. If we go to our data, we have our training data set, and that has the board and the score and the best move. But then in our test data set, we just give you the board. So this is 200 additional new board states that we haven't seen yet. And so that's actually what we need to make predictions for to actually compete in our competition. Notably, for this competition, the rules state you can only submit predictions that you built the model for. So you can go and download lots of models that'll give you really great results. But we're going to consider that cheating, and you will not be eligible for a swag drop if you get a high score from that. And I could just request to see your notebook. So like don't try it. It's not a good time. Okay, right on. So we are making predictions and submitting. We have run this and generated a model for ourselves. And boom, we see our loss during training. That looks good. This is still really small. But so now we will read our test set in. So we kind of use the analogy of the training set is kind of your study guide, the validation set is kind of a quiz, and the test set, like this is the big exam, right? So we see we just have our IDs and our board. We can do basically just apply our play function to all of our boards. So all this line is saying is run our play neural network on all the boards in the testDF, and then keep the results in a new column called best move. This will take a second. I think now it'll take like 16 seconds or something like that. But this is with a really small neural network. So if you make this beefy, it might take 10 minutes to actually make predictions on all of these. It's running, it's thinking about it. Boom, okay. So let's just double check what came out in best move. And hey, we have a bunch of actual moves predicted. Now, I don't know how good they are. It's still learning. It's a really small brain. But so now we can actually prepare this to actually make a submission. So we can to make a submission, you have to have both the IDs and the best move that you predict. And we can make sure this looks like our sample submission. So we give you a sample submission in the data set that shows you something like this. So we want our output to look like this. And when we compare our submission to the sample submission, they look like they're in the same format. Now, the sample submission it always predicts A2, A4. So the sample submission is not actually a good submission. I think it would give you a score of 0. But this submission that we came up with, it is of the same format, but we have better, hopefully, better predictions, right? So our IDs are all the same. They're in the same order, but our predictions are different. And so now the only thing we have to do to submit is to do submission.toCSV, and then say index equals false. So it'll lop off the sort of fake index we created. And now if you click over here, you should see our submission plopped out. So this is our submission to the competition. And if we feel good about it, we can come over here and hit submit. So if you hit submit, also notably, if you're following along, this is all you have to do to be considered in the random draw for a swag drop. So we can hit submit, and it's queued up, and it's running. And after hopefully not too long, hopefully just a couple minutes, it'll actually tell us what score we got. And hopefully that'll be a good score, you know? Oh, also notably, the number that you will see when you submit is your accuracy, meaning what percentage of your predictions were the same as like the actual best move, right? And so this should give you some indication of, notably, there are just, like we said, there are 4,000 possible moves in chess. So if you get a low accuracy to start out, don't feel bad about that. In fact, I think I've submitted this before, and yeah, the score that this thing gets if you just submit it is 0.08. So like 8% of the moves that you recommend are actually the best move. Which, you know what, makes sense. It's a small model. We didn't train it for that long. I'm not actually that surprised by this being our score. But you can actually click on this to see sort of a live update of it running. So you can see, okay, the logs are kind of a mess, but you can see we're still training. We're on epoch 15, and that should take a second. But after this, I think we will call it a night. And you basically have the whole week to try out different things. I have one particular thing that I'm kind of interested in trying out, and that's what we'll be looking at on Friday. And we'll also recap, I believe technically actually we're calling it, and when we're finishing the competition on Saturday. And so then I will hop on Discord and let folks know sort of who won and who's getting swag dropped. So boom, there we go. We made a prediction. We submitted our form, or we submitted our submission, and we got 0.08 as our score. Which maybe we got 15 or 14 minutes left. One last thing we can try is, what if we just and no guarantees here, but what if we just made our model bigger, gave it some more data, and gave it a little bit more time to train? So what if instead of 10,000, we gave it 20,000? What if instead of 128, we gave it 1,024? And what if instead of 20 epochs to train, we gave it 40 epochs to train? Which notably, this should mean that it'll take a lot longer to train, right? Like we double a lot of numbers. So it'll run for a second, and then it'll take another second to submit. but like it'd be really cool if we got at least a little bit better accuracy, right? It's thinking about it. Okay, so earlier it was just zoom in, and now it's like, it takes what, 5 seconds per epoch, which, I mean, in a lot of training processes, that's still considered pretty fast, but this is still a lot slower. It was like half a second per epoch before. So we could maybe jump ahead and just submit and see what we get. So version 5. So every time you make a submission, you'll get sort of another version number, and we can see what happens. On that note, we can check back if it finishes, if the submission finishes before the stream is up, we could check back in on it. But on that note, do we have any questions, any comments? Are folks excited? How was the speed? Anything that you'd be excited to cover on Friday? Oh, that was tragic. I think my internet connection is getting a little bit funky. All right. Well, I don't want to just keep stalling, and our thing is still running. Oh, okay. What is there else to do? Maybe that's it. Maybe we just call it, and maybe everybody can on their own time see how this does. I guess we should take a look at the. Ezreal is excited to try some things. I'm pumped to see you try them. Okay, so maybe something we could look at is just one little recap on sort of the competition space. So we have our overview here with all of my notebooks. You can see the data on the data slide, but usually you'll just want to play with this in a notebook. You have sort of my examples, and you can always click on these to make a copy of them and play around with yourself. Part 3 is probably the one that you are going to want to fork. It's probably going to be the most helpful one to mess around with and try. And then also, if you have any questions that you want me to answer between now and Friday, please drop them in the discussion section, and also talk to one another. We're here to build the hacker community, and helping one another out is lovely. And then finally, oh great, oh my goodness, Aiden, I'm so glad that you jumped in and made a submission. So you can see the leaderboard here. And so the highest score that is not cheating will get a swag drop. 2 other people on the leaderboard will get swag drops. And then the notebook that someone has released that I like the most will also get a swag drop. That's 4 chances for swag drops. And then finally, in terms of rules, the big one is MLH code of conduct, and then also you can't use a model that you yourself didn't train, because that would be rude, right? Other than that, I think that's where we're going to leave it, and we will leave a little buffer of 10 minutes for whoever's next to jump on. But thank you so much for being here. This was a blast. It was a blast to have you. Ezreal, I'm glad the pacing was good. Thank you so much for your questions. The engagement was great. And we will check back in. Oh, on Wednesday at this same time, tune in to see me and my boyfriend play a game drinking coffee together. That'll be an interesting, wacky time. And then finally on Friday, join, and we will look at some other ways to build models. We'll look specifically at something called ensemble models, and then we'll do sort of our final push to see how the competition is going, and hopefully see who's in the lead. So. Thank you for checking in. Someone's asking about a Twilio promo code. I would say check Discord. Ask folks on Discord would probably be better. I'm not familiar. Oh, Bananarama Twitch. I'm so glad you feel like you're getting an understanding of ML. Ezreal, thank you so much for being here. And on that note, I think we will call it a night, and I will play you out on Kalimba. Happy Monday, happy Global Hack Week, and I will see y'all in 2 days.